Okay, so you guys are here for CPG 586 Deep Learning course. And I'm Professor Mahmood, so hopefully all of you know me. And my office is in Tech 232, and email my last name, mahmood@bridgeport.edu. Okay, so let me give you an idea of what exactly is deep learning and what kind of things we'll be doing in this course. So if we take a look at the field of artificial intelligence, okay, the way it started is, I would say in the mid-'80s, somebody came up with the idea of artificial neural networks. So they introduced how a neuron could be set up to compute something, how a neuron can learn, right? And everybody got very excited about this field. And I also looked at it around that time, and everybody was talking about, this is again more than 40 years ago, that this will be the great technology and so on. But then something happened. Early 90s, everybody lost interest in it. Okay. So the field of neural networks pretty much died. Okay. So the question is why? So I'll answer that in a few minutes. Then somewhere in 2007, 8 time frame, all of a sudden, everybody said, oh no, let's go back. Neural networks are great. They can, do artificial intelligence. And so the field of AI got totally revived. So just like anybody else, I also had given up on neural networks. So 2000, 2007, 8 timeframe, I said, oh no, there is something more to it that we missed. So I also started following AI quite a bit, started doing research in it. And I strongly felt that now, meaning at that time, this technology had great potential, okay? And for around 2015, 16, I started talking about we should start a new department in MS in artificial intelligence. So we filed for it, I think 2018 or something like this. In 2020, we got the program approved from state of Connecticut. You have to go through a formal process to get a program approved. And I think we were one of the very first ones in state of Connecticut to start offering an MS in AI. Okay. So as part of the learning of AI, the course of deep learning, in my opinion, is the foundation of AI, as you will see as we go along in this course. Okay. Once you take this course and develop a very good foundation, then of course we have a lot of very, very good courses. Some of you are in natural language processing and large language models. We have computer vision, autonomous vehicles, reinforcement learning, advanced deep learning. Next semester, I'll be teaching a course which is quantum AI. Quantum computing is the next future. How can it be combined with AI? So the field is amazing. Some of the research, some of the things that are coming out is truly mind-boggling in the sense that it is so simple, okay? But it's able to match or surpass human intelligence in many cases. So how could that be? So that's our goal, to develop that excellent foundation through this course, okay? So that we can get to the top of whatever is the state of the art in AI. So that is the goal of our course, right? So, okay, so coming to our deep learning course. So before I come to the deep learning course, let me clarify this, what happened over here. Even though we knew neural networks 40 years ago, how come everybody lost interest in it? And how come we are back to saying, oh, no, they are really great. And you can see with ChatGPT, it really does work, right? So as I go along in today's lecture, I'll clarify that nicely. Okay. So as far as the deep learning course is concerned, last time I taught this course was as a live class, was in 2020, if I remember correctly. So the course website where I'll be putting the recording of the lectures, the material is http kiwi.bridgeport.edu / name of the course CPEG 586. I think right now the username password is ubstudent 2018, but I will change it to 2022 because for those of you who are taking, for example, other courses, that's the password I use. This way you won't have to, get confused which one is which. Okay. So anyway, if you go to this website, so if I take you there, okay, so this is what it looks like. So sorry, last time I taught it as a live class was 2021. So anyway, if you take a look over there, UB student. UB student 2018. So if we take a look at 2021 lectures, okay, so you'll see it starts out with some introduction, which I'm doing right now. Then how do we create one neuron? Then how do we create more than one neuron? And what's the theory of it? How do neurons learn? We'll go over this. And then gradually we'll make it more and more involved. Hundreds of neurons, thousands of neurons. Then there's a concept called convolutional neural networks. How do they work? How do we set up? So from a learning point of view, like I said, because this is the foundation of our all AI knowledge, in my opinion. So the way we will learn it is the half of the course, we will learn different concepts and we will program whatever the concepts we are learning of all these different concepts from scratch. So for example, there's a concept called softmax. There's a concept called batch normalization. There's a concept called dropout that we use in neural networks. So we won't use any library. We will implement it ourselves using Python, okay? So that we really understand how does it work, okay? So that half of the course, all networks we create will be completely without any library. Of course, we'll use the NumPy library, which is a matrix computation library in Python. But other than that, we will not use any AI library, okay? So after we have mastered the foundation of how do these different concepts work, how do we program them, then the second half of the course, meaning the last part of the course, will make it slightly more advanced and start using libraries, okay? If we go back 3, 4, 5 years ago, there was a library from Google called TensorFlow. It was very popular, okay? The only problem with TensorFlow was they had a version 1.1, 1.2, 1.3, right? And it was a pain to program in the sense that we are used to programming normal programming languages such as C, C++, Java, and so on, where you write something at some point in time, you call a function, pretend this is a function, It will execute the code, then come back over here. So what I mean is there's a certain flow to the program that we are used to when we learn any programming languages. So this old TensorFlow was really a total mess. The workflow, meaning the way you wrote the code, was not very natural, okay? So they did try to make it easier in the version 2 and onwards, okay? However, at the same time, Facebook introduced this library called PyTorch. And PyTorch is like a normal programming language. You write functions, you call functions, you write classes, okay? So as a result, the research community, meaning, all the top colleges, they abandoned TensorFlow, they went to PyTorch. So all the research that was being done, other than Google, was being done in PyTorch, okay? So I myself started out with TensorFlow. Then, 4 years ago, I switched to PyTorch. And these days, any research paper that comes out pretty much is in PyTorch. So I'll introduce to you PyTorch library after we have mastered all the concepts, all the foundational concepts. Then we'll start to program neural networks, convolutional neural networks. I'll also introduce to you what are transformers and how can we program them. Okay, looking at just to give you a roadmap of the AI technology. So as we program and develop AI, so the models, so we refer to a term called model, which is really the core engine which will do the AI for us. So from an architecture point of view, like whatever model we are creating, what architecture will it be following? Like I said, it started out with neural networks. We still use neural networks, okay? For simpler things, if computer vision is involved, convolutional neural networks is what we use, okay? But gradually, for natural language processing and large language models like ChatGPT, right now it's all transformers. Even for vision, so this is for NLP, this is for vision. Okay, even for vision, now the transformers are also very competitive, in some cases surpass convolutional neural networks, right? One of the latest in this field is, and I'll give you a slight idea towards the end of the course, in the advanced deep learning, we'll go in more depth. There's another architecture which has foundations in the electrical engineering control system theory, is called state space models. Okay, abbreviated as SSMs. So here there's an architecture. If you go home, try to Google Mamba, is attracting a lot of excitement, okay? One of the reasons it's attracting a lot of excitement is, for example, if you take a look at, a transformer-based NLP model, such as a ChatGPT, it requires tremendous amount of energy, tremendous amount of compute power to be able to train a system, right? So one of the focus in the latest research is how can we make these more efficient so that, because we are training these on trillions of data. So if we have to wait 2 months and spend hundreds of kilowatt hours of energy, every time we, try to add more knowledge to it, we have to retrain the whole thing. So, which is very, very energy and time consuming. So how can we make it more efficient? So one of the reasons state space models are attracting a lot of attention is they are hundreds of times faster than the transformers. Okay. Do they work as good as the transformers? Okay, some people claim, obviously the people who are behind this technology are saying, no, they work as well. Okay, But OpenAI and Google and Microsoft and Facebook for their large language models are still using transformers. They have not switched. You won't see ChatGPT being implemented. Perhaps those guys are looking at how the next generation could be, because everybody wants to be more efficient, time-wise, energy-wise. So anyway, because this is a foundational course, at least what is the fundamental idea in all of these? You should have a good idea, okay? And then, like I said, after this course, hopefully you will take the advanced deep learning course where we go into more in depth and see the applications of this, the advancements within each one of these architectures. So anyway, in the second half of the course, as I introduce PyTorch, I will also go into these different architectures, okay? The field of AI is changing extremely, extremely rapidly, okay? So like I said, last time I taught this course was in 2021. And even though this is a foundational course, meaning the first half of the course has not changed. We still use, for example, backpropagation, which is the fundamental algorithm for training a neural network. So all of these will use backprop and forward and loss functions. So all of these will use dropout, normalization. We have optimizers such as Adam and so on. So those are covered in first half of the course. So those stay the same, okay? So after today's lecture, this is a hybrid class, meaning sometimes I'll give you guys a lecture. Sometimes you will watch the recording of the lectures, okay? So some of the lectures, especially in the first half of the course, because they were already recorded in high definition, I will not repeat the same thing you will go through. And especially the second half of the course, then I will start to update the course and give you whatever is the newest information with respect to these architectures and so on, right? So I will email you or via Canvas, let you know if we will have a class, or are you expected to go through the recorded lecture and do the assignments. If you take a look at our course, let me go back to. Hey, so again, 2021, when I gave the assignments, for example, I think the first all of these assignments I think are valid. So if you can go ahead and if you wanted to, be a little more ahead of the class, you can start doing the assignments. What I will do is, because they're all very, very good assignments, I will add 2, 3, 4 more assignments at the very end, so that you can play with some of the newer things that I mentioned to you guys, right? Okay. So what kind of background do you need to be really good in AI? AI requires some math. And even though the mathematics can be advanced at times, okay, but behind every advanced concept, there's a very simple way to understand it. So as you will see throughout, if we need some more involved mathematics, I will refresh your memory. So don't worry, even if you said, oh, I forgot how to do the derivative or the integrals or, differential equations, don't worry, I will simplify it so that the concept makes sense. So gradually, not only the mathematics, also the statistics is very important, because if somebody asks me, what is AI? Okay. Or let me ask you guys, how would you define what is AI? If you were to say one sentence description of what is AI, anybody wants to volunteer? Yeah, very close. So AI is learning from data. See, unlike all of our fields that you guys learn in engineering or computer science, we try to formulate everything via mathematical equations. Okay. In AI, we start out with just raw data. Okay. For example, natural language processing, like ChatGPT, how is it trained? Nothing special. The training is extremely easy. If you take a look at ChatGPT, which I'll go over a little bit of it, the way we train it is we start going through a lot of text documents, okay? Whether that is Wikipedia articles, whether that is newspaper articles, whether that is books, okay? And we just start feeding to our model just the plain text. And just by looking at sequence of words, remember all the Wikipedia or news articles is just a collection of words. The model implicitly learns how do we form sentences, what word should come after which word, uh, not only sentences, then paragraphs, and then from there, it also develops the intelligence. Okay, so as you can see, ChatGPT is just pure and simple. We don't say, hey, here's a complicated equation, follow this equation. No, we just say, here's the data, you figure out internally what will be the internal mathematical mechanism to be able to predict, for example, the flow of words in a sentence or in a paragraph, right? So AI is all learning from data. The other thing you should remember is the more data we have, the better will be our AI model. Hey, so sometimes, there's a question, you will hear this word machine learning, AI, deep learning. So what's the difference between all of these? Okay. AI is the big umbrella. Underneath it, we have machine learning, we have deep learning as an example. Machine learning sometimes is mixed up with, deep learning or AI, but the slight difference that, generally what people follow is in machine learning, generally we have less data. Okay, so we do not create these deep neural networks or convolutional neural networks or transformers. In machine learning, we try to come up with mathematical equations, which are again learned from the data. So we have, concepts like logistic regression is one of the algorithm. Okay, so that we can have it, differentiate between two categories of data. As an example, we have support vector machines so that we can categorize data into different, right? So similarly, we have decision trees over here. So there are a lot of interesting algorithms, but generally, these algorithms are able to learn with relatively small amount of data and do a good job. Okay. But if we can have more data, then the best results we will get will be via deep learning, via deep. So what exactly is deep learning? So, okay, so let me now go into a little bit idea of deep learning. Hey, so if we go back to the history of neural networks, right? We started out with defining a neuron. So let's take a look at what exactly is a neuron. Okay, computational neuron or artificial neuron, even though when we created these, we were trying to model the neurons in our brain, But then later on, we realized, no, our brain's neurons do not really work like the artificial neuron, but it doesn't matter. It still works in some cases as good, in some cases even better than our human brain, right? So a neuron, as you will see, is the architecture goes like this. Okay, this symbol in math basically means sum or summation. Okay. Then we feed it to what we call a sum function, and we call it an activation function. And then this is our output. Hey, the sum function can take many inputs. Usually we use the letter X as the input. So for example, our input could be 2 inputs. Input could be 3 inputs, 4 inputs, 5 inputs. So depending upon our data, however many inputs we have, we'll feed it to our sum unit. As we feed it to our sum unit, it will multiply by a number, which we call the weight. So this is called the weight, right? So W0, W1, W2, right? We also will feed in 1. This will get multiplied by what we call B. B is referred as the bias, okay? So this is the general architecture of a single neuron. So now if we put this in a circle or a ellipse or whatever, this is what we call a neuron, one neuron. Okay, so in the beginning, the weights are randomly initialized. So for example, in our case, W0, for example, could be, let's say, and typically we initialize them as less than 1. Okay. For example, W0 could be 0.1, W1 could be 0.3, W2 could be 0.4 as an example. Okay. So now let's take a look at how will it produce the output. Okay. Suppose at some point in time, our data, remember data is X0, X1, and X2, okay? So suppose we feed in 1, 2, and 3. X0 of 1, X1 of 2, X2 of 3, right? So the question is, what will be the output produced from our neuron, okay? If this is how the weights were initialized, as you can see, what will happen is, we'll multiply this 1 with W0. X0 is 1, right? Which is 0.1. So you can see over here will produce 0.1, right? Then 2 times W1 is 0.3. So this will make it 0.6. And similarly, X2, which is 0.4, 0.4, sorry, X2 is 3. 3 times 0.4 will be 1.2, right? So what is the sum unit going to do? It's going to add up all of these. So what will be the answer? 1.9 will be produced over here, okay? So this 1.9 will be passed through what we call an activation function. And we have different activation functions. For example, one of these is called the sigmoid. Okay, sigmoid has an equation 1 over 1 plus e to the minus x. Okay. So if we plot this equation for the sigmoid, if this is x, okay, this is what it looks like. It goes, okay, maximum value c, for example, if you pick x to be a very large number, what will happen? E to the anything negative large number is what? Very close. See, what is e to the minus 100 as an example? Isn't it same as 1 over e to the 100? So 1 divided by a large number is what? 0, right? Very close to 0. So you can see when x becomes very large, this part will become 0. So what will be the answer produced by the sigmoid then? It produces this whole as an answer. 1 over 1 plus 0 is what? 1. So you can see as x increases quite a bit, the answer produced is 1. Okay, very similarly, what if the input to the sigmoid is a large negative number? So if it is a large negative number, let's say it's negative 50, then what will happen? This minus minus will cancel. So it will become 1 over 1 plus e to the 50. E to the 50 is a huge number. So what will happen to the whole thing? It will become very close to 0. So you can see as we go negative, the value of the function becomes 0. Okay, so sigmoid has this equation. It goes 0 to 1. As x increases, it becomes very close to 1. As x decreases, becomes negative, it becomes 0. And at the halfway point, for example, if x is 0, so let's take a look. If x is 0, what will happen? E raised power 0 is what? Anything raised power 0, if you remember from your math, is what? 1. So you can see function will become 1 over 1 plus 1, which is half. So when x is 0, which is right at this y-axis point, the value of the function is 0.5. Okay, so if we are putting an activation function as a sigmoid, and we pass the sum unit produces 1.9. So my question is, roughly speaking, what will be the output then? See, 1.9 pretend is somewhere over here, right? So you can see it may be slightly less than 1. Okay, it could be, I don't know, 0.85 or 0.87, something like this will be the output. We can find out exactly by plugging this 1.9. So if you did 1 over 1 plus e to the minus 1.9, whatever that value is, that will be output over here. I'm just assuming, let's pretend that is, we can calculate it exactly. So this is how one neuron works. Okay, the weights are in the beginning, they are random. Okay, as we train the network to learn something, these weights keep changing. Okay, once it's fully trained, we fix these weights, then they will not change. Based on whatever the final value of the weights is, we'll just feed in an input and it will produce an output. Okay, so that's how a single neuron works, right? So next question is, how do we make it learn? Okay, how does a neuron learn? How do we change these weights? Okay, so the answer is, so now let's try to answer. And again, before I go to multiple neurons, let's just take a look at a single neuron. How will we make it learn, right? Okay, so in the field of entire AI or deep learning, it doesn't matter. We will create some network. This network could be one neuron or many neurons. Okay, pretty soon I'll show you we'll create many neurons, right? We'll feed to this network some input X. So X is our input. Okay, it will produce some output, right? For example, in our previous case, we assumed the output produced was 0.87, right? Okay, for it to be able to learn, we have to have a target. Target basically means what do we want it to produce, okay? So sometimes I call it the expected output. And let me call whatever output it produces as the actual output, okay? So we'll take so the expected output will come from the training data. Okay, the actual output is being produced based on the input. As I mentioned earlier, in our example, it was 0.87, right? So then what we will do is we'll take the target and the actual output, feed it to a very special function, which we call the loss function. And I'll give you an example in a second. The output of the loss function is always just a number. Okay, one number. Okay. So first thing we will do is in our learning of our network, we will feed the training data. So our training data will always be as a pair. There will be an input X and there will be a target. The X we will feed over here. The target will go over there. And so based on this X, like I said, it will produce an actual output, which the loss function will compare with the target and determine a loss. Okay. Then, so we will go forward through our network, whatever network we are creating, meaning we feed in X, it will, as it goes through the network and the loss function, it will produce some value for the loss. And I'll give you a quick example in a second, but let me give you the high level idea. After it has produced some loss, right? So like I said, the loss is basically comparing how far the actual output is from the expected output, okay? As the network learns, we want the actual output to be same as the expected output, okay? For example, one of the loss could be subtract the target from the actual and square the two. Okay, for example, in our previous example, what was the actual? 0.87. Okay, let's pretend we wanted the target to be 0.9 for whatever reason. Okay, so suppose from our training data, we know if we feed in x0, x1, x2 of 1, 2, and 3, we wanted the output to be 0.9. But what did it produce? 0.87. So if the loss function is simply what we call mean square error, okay, subtract the two and take the square, the squared error, right? So as you can see, 0.9 minus 0.87 will be 0.03. If you square 0.03, what will you get? 0.009. Okay. So that is our loss, right? So now what we will do is whatever that loss is, we'll go backwards. So in the backward pass, what our goal is to adjust the weights so that next time the error becomes even smaller, okay? So the learning process, what I'm trying to say is feed the data, feed the training data to the network, produce the loss, okay? Whatever that loss value is, because do we want this loss to be high or loss to be low? once it has learned, right? Once it has learned, we want actual and target to be exactly the same. So what is the ideal loss? 0. Okay. So if it is high, we need to go backward and adjust the weights over here. Okay, if it is low, we will still adjust it, but slightly. If it is very high loss, we'll adjust the weights even more, right? So to show you, and like I said, it doesn't matter whether it's whether it's a single neuron network or million neuron network, or it's a transformer, or it's a state space model. We'll follow this exact same philosophy in training all of these networks. So understanding how it's learning, how it's training is very important. Okay. So let me give you a more intuition into how will we adjust the weight. So the question is, how do we know what to change each weight to? Okay. Should we remember in the beginning, what were our weights? See if I go back over here. When we randomly initialize, weights were 0.1, 0.3, and 0.4. So if we get a loss, the question is, how will we change it? We'll make it 0.2 or 0.15 or 0.12. How do we know that whatever change we make will make it learn better and not make it worse? Okay. So now let's try to understand the theory of these loss functions. Okay. So if you take a look at, let me refresh your memory of a little bit of math, right? Suppose, let's sidetrack. You are given a function, y equal to x minus 2 squared. Okay, and let's try to plot it. Okay, so if we plot it, if this is our x-axis, this is our y-axis. Okay, when will this have a y be 0? 2. Okay, so anyway, now if you start picking a value of x, so for example, if x is 1, you will see 1 minus 2 is -1, negative square is 1, so y will be 1. So anyway, if you try to plot it, all these values, what you will see is it will come out to be a parabola. Okay, if for example, at x of 1, the value is 1, right? What about x of 3? It's still 1. So as you can see at 3 also, it is 1. And that's why it's following this parabola. Okay. So if you take a look at this loss function that I wrote, loss function, I said one of the loss functions might be target minus actual square, right? So if I try to plot this loss, what will it look like? Like a parabola, okay? So now let's say we have some weights on the x-axis, okay? And let's say this is our loss. So this is our loss, okay? In the beginning, the weights are randomly initialized, okay? So the loss may be high. There are two possibilities. How we initialize the weights in the beginning, the loss may be over here, okay? Or it could be on the right side, either way, right? Okay, so let me pretend we initialize the weights. So this is how the initial weights were. Okay, and the loss happened to be some value over here. Okay, so my question is, if we go this way, we are increasing the weight, right? Because x is becoming x-axis, it's going higher. If we go this way, what's going to what is happening to the weights? Decreasing, right? So my question is just looking at this picture. If in the beginning, the loss is right here, This is the value of the loss. Okay, what's our goal? To increase the loss or decrease the loss? Decrease. So what should we do to these initial weights? Reduce them or make them bigger? See, which way should the weight move so that the loss becomes smaller? Go left or go right from here?
Go right.
Go right, right? Because see, if I go a little bit to the right, you'll see I'll get over here. Is the loss decreasing or increasing at this point compared to this point? Right? So as you can see, we have to increase the weight. Okay. So you guys will remember from your basic math, if I give you an equation for the line, right? How do we know how quickly this line is increasing or decreasing? Remember, if we say dy over dx, that is the derivative, which is basically change in y divided by change in x, right? Or in simple terms, that's the slope. Okay. Which one of these three lines has a higher slope? See, this is x, this is y, right? So see, as it's increasing rapidly, the slope is higher, right? Positive. Here, the slope became less. What will happen if it is totally flat? Change in y is 0. See, if you pick any 2 points, right? What's the change in y for these 2 points? 0. Change in x, let's say x was 1 over here, x was 2 over here. So you can see change in y is 0, change in x is 1, 0. So slope is 0, right? So what I'm trying to say is the slope or the derivative gives us an idea of how fast is it changing, okay? So how fast is it changing? So now take a look over here. Let's say this was the loss in the beginning, okay? If you remember, derivative is basically if you draw a tangent at that point. So like if you pick over here, draw a tangent, the slope of that tangent tells you how fast the curve is changing, okay? So if I took the derivative over here as compared to the derivative somewhere over here, which one is changing fast, over here or towards the bottom? Which one has a higher slope? The top part or the bottom? Bottom, right? So as the curve starts to flatten, the change is becoming less, right? The slope is becoming smaller, right? Okay. Also, you will know, for example, your basic math. If I'd show you a curve of a line over here, is the slope positive or negative? Okay, see, the way you find out is you pick 2 points, okay? So for example, let's say this is 1, this is 3, this is 2, this is 4, right? So at this point, for example, x is 4, y is 4, x is 3. So change in y is 4 minus 2 between the 2 points, right? Change in x is 3 minus 1. So you can see as x increases, the y increases. So that is a positive slope. Or we will say dy over dx is positive. for this line, right? Okay, what if the line is opposite? Okay, so now again, if you pick 2 points, change in y divided by change in x, so you'll see, for example, here, for example, again, let's pick 1 and 3, 4 and 2, right? Okay, so what is change in y? Sorry, 4 and 2, 4 minus 2, right? So at this point, what is x? 1 minus 3, right? So you can see the slope has become negative now. So if we are, as x increases, the value decreases, that is a negative slope, or we will say the derivative dy over dx is negative. Okay, so in our learning of our neural networks, what we do is the loss function is a parabola, okay, if we use the mean square loss, okay? If the weights were initialized, for example, as I showed you right here, if this is where the initial weights were, then the way we will change each weight will be W of I equal to the old value. So W of I old, okay, minus, we will have some lambda, we call it a learning rate, times partial L over partial W of I. So this is how we adjust the weights during the learning process. So let me see if this makes sense. Okay, this partial L over partial W of I is basically the slope of the loss function with respect to the weight. Okay, so my question to you is, let's go to our example. If you take a look at if this was our start point, what is the slope of the loss function at this point? Is it positive or is it negative? What was it? Positive or negative? Negative, right? So let me assume at that point, this is negative 0.2. Okay, for the time being, don't worry about the learning rate. Let's pretend it's 1. Okay, so what are we doing to the weight then? Oops. Okay, so remember, we said this will be W of I. So the old value, let's pretend, was 0.1. Okay, minus learning rate is 1. The slope that we are assuming is negative. So let's say it's negative 0.2. So you'll see this will become negative 0.2 over here. So what will happen to the old value of the weight? Will it increase or decrease? See, negative multiplied by becomes positive, right? So you can see what will happen to the new value of the weight. Old value was 0.1. It will get added. It will become 0.3. So remember, that's what we discussed. Looking at this picture, if we want to decrease the loss, we have to increase the weight, okay? So that's why this negative came out, because if the slope is negative, we want the old value to be added a positive thing so that the weight increases and it decreases the loss, okay? Let's take a look at the other scenario. Let's pretend we initialize the weights. Remember, the weights are initialized randomly. What if the weights were initialized somewhere over here? Those were the initial weights. Okay, forget the math. First, tell me if these were the initial weights, should they be increasing to decrease the loss, or should we be reducing them to decrease the loss? You can see we have to move this way, right? Because this is where the best loss is. So we have to move the weight this way. What does that mean? Decrease it, right? So now tell me at this point, is the slope positive or negative? It's positive. So you can see what will happen now, Wi minus the learning rate times the slope is positive, right? Whatever that number is. Let's say it's 0.3, 0.4, whatever that is. So what are we doing to the old value of the weight? We are subtracting from it some number. So we are moving the weight to the left, okay? So that's how we make the neural networks learn, right? So let me summarize it. So like I said, it doesn't matter how complicated our network is, whether it's a single neuron, hundreds of neurons, whether it's a convolutional neural network, whether it's a transformer, whether it is a state space model, all of them will follow the same policy. What is the policy? We will have a training data. Training data means we know the input and we know the expected output. Let's call it T as the target. So this is the expected output. And I'll give you more examples of how do we know what the expected output is, okay? So I'll give you a few examples. So anyway, we will have a lot of this training data. And again, X could be a single number. In our example, we said X0, X1, X2. There were 3 inputs. Collectively, I'll call them X. Okay. So it doesn't matter as long as we know what the inputs are, what is the expected output correspondingly, right? So then we'll set up the network. We will initialize the weights randomly. So randomly initialized weights. Okay, we'll feed in X. Okay, it will produce actual output, whatever that output is. We'll compare that with our target, which we know from the training data. Then we'll come up with the loss function. Based on the problem, we'll pick a loss function. Okay. It does not have to be a square difference. Okay. It could be, you know, for example, as we go along, we'll come up with different loss function. It could be absolute mean error. It could be cross entropy. There's a logarithmic relationship. It could be something we come up with our own complicated formula, right? Whatever the loss function is, important thing to remember is loss function always produces one single answer, okay? It is always one number. Okay, so typically, like I said, you can think of the loss function like a parabola, okay? So our goal is it doesn't matter where the randomly initialized weights were initialized. We want to move them gradually so that the loss becomes close to 0. And once it's 0, the network is fully trained, and then we will stop the training. Then we'll feed it any unknown data, and it will produce whatever output it produces, the prediction from our network, okay? So that is the main goal over here. And what is the learning equation? Learning equation, like I said, it depends on the slope of the loss function, okay? With respect to weights. See, if you have 3 weights, with respect to a loss, it becomes a 3-dimensional problem, okay? If I have 100 weights, it becomes a 100-dimensional problem, okay? I cannot draw for you even, a single dimension, or in this case, if I had a single weight, I can draw it, but if I had two weights, I could still draw it like a 3D picture. But beyond that, we cannot draw it out. But conceptually, you can see what the concept is. So the concept is, doesn't matter where we initialize the weights. If our learning equation is take any weight, okay, subtract from it the lambda, which I mentioned is the learning rate, times the slope slope of the loss with respect to that weight, okay? Which we call the partial derivative of the loss with respect to WI. For every weight, we'll keep doing this, okay? So now the question is, why do we have this learning rate? And what should be the value of it, okay? See, typically what we do is we pick this learning rate to be small. Okay, for example, it could be 0.01. Okay, why do we pick it small? Because we want to make a small change to our starting weight. Meaning if we were over here, we want to gradually move so that the loss is decreasing. So you may be saying, well, wouldn't it be a lot faster if we just took a big giant step over here? Then in 2 updates, we'll reduce the loss to 0. Okay, and the answer is, in simple cases, it may work, but sometimes what happens is, let me draw it again. Okay, you were here. Okay, you made a big change this way. Okay, so you may end up over here. Okay, so now that you made another big change over here, you may end up over here. So you just keep oscillating back and forth, and it never reduces. But if we reduce it gradually, we make sure that we will come very close to the 0 loss, okay? So there is an optimal learning rate given a problem. And this is, as you will see, it's data dependent, problem dependent. A lot of research has gone into how should we adjust the learning rate so that it learns properly, loss keeps decreasing, does not oscillate, and also is efficient. Because if we make it too small, then what will happen? We'll just take hours and hours to, computation to reduce it. So one of the lectures will talk about learning rate optimization, as you will see. Okay. All right. So now let's go further into it. And let me give you a tiny bit idea now. So suppose, let's go back to a single neuron problem. So your first assignment, you'll be programming a single neuron so that it can do the learning. So let me show you what problem we will create. So let's say we wanted to recognize, so we want our single neuron to classify if a given point in 2D space belongs to, let's say, blue or green category. Okay, so we'll create some artificial data ourselves. So let me show you what our data will look like. Okay, so you'll be given bunch of XY coordinates. So let's say here is blue. So you're given some points. Okay, some are, let's say, green, some are blue, right? And let me assume the distinction boundary between the two blue points and green points is controlled by a simple math equation, y equal to 2x plus 0.3. Okay. So if the point is above this line, this y equal to, which is defined by y equal to 2x plus 0.3. If the given point is above the line, then it belongs to the blue category. If the point is below the line, then the point belongs to the green category. So that is our given problem, okay? So let me give you an example. Okay, suppose I give you, for example, x of 2 and y of 4.5. So my question to you is, if you already knew that this is what is the decision boundary between the two categories, should this point be belonging to blue category or green category? See, how will you find out? If x is 2, if I plug in 2 over here, so let's say x is 2, right? So according to this equation, y should be 4.3, right? So 4.3 is exactly on the line. But what did somebody tell us? 4.5. So is it above the line or below the line? So what category should it be? Blue. Okay. Very similarly, let's say somebody gives us x of 3 and y of 5.9. So see, y of 3, x of 3 will make it 6.3 will be exactly on the line. But what is y given to us? So it's less than 6.3, right? So it is green category. Okay. Now, in this example, I already told you this is the equation of the line. Okay. But let's pretend to the neural network, we never told it that this is the equation of the line, okay, which separates the blue and the green category. All we did is we created training data. So let's take a look at what our training data will look like. So let me create some training data. So our training data, like I was saying, has X and a target. Okay, sometimes the target is called Y. So it may be confusing in this problem because Y is the coordinate of our input, right? So what we will do is we will break this x0 and x1. So as an example, for my first example, if x0 is 2, so think of x0 as really x. X1 is really y in our two-dimensional picture that I drew, okay? And target is the decision. What we will do is if it is above the line, we'll produce an answer of 1. If it is below the line, we'll produce an answer of 0, okay? Because see, neural networks or all networks, as you will see, they operate on numbers. We cannot say, tell me it's blue, tell me it's green. The 1 and 0, we can, further translate it to blue or green, but to a neural network, it will always be fed as numbers. Okay, so let's see if everybody understands how the data will be generated, training data. So x of 2, y of 4.5, which means x0 is 2. The second input is 4.5. What will be the target then? No. Target is like 1 or 0. If it is above the line, it's 1. If it is below the line, it's 0. So you can see this 4.5 is above the line, right? 4.3 was on the line. So what is the target then? 1, right? Similarly, if I create the data 3, 5.9, what should be the target? No, remember 6.3 will be on the line. So 5.9 is, so just put this in front of you that based on this, we are deciding the target. If it is above, it's 1. If it is below, it's 0, right? Okay, let's pick another example. How about 1 and 2.1? What should be the target? 0, right? Because it's below the line. 2.3 will be exactly on the line. Okay, how about 1, 2.4? 1, right?
1.
Okay, let me pick another example. 5, 10.1. 0, right? Because again, if you put 5, 10.3 is exactly on the line. If the second input is, which is the y actually, remember this x1 is the y, right? Okay, so anyway, so this is how we will create a lot of training data. So this is our training data. Like I said, training data goes into X and the target, which sometimes we call it as Y. Okay, so Y is really our target. So don't get confused with, oh, Y was the coordinate of the point. The two coordinates or the two inputs to the network are X0 and X1. Okay, so if I wanted a single neuron neural network to learn this distinction between blue and red category, which are defined by this equation y equal to 2x plus 0.3, right? I will create some training data like I showed you over here. Okay. Now the neural network that we will set up, oops, sorry. Okay, neural network that we will set up will look like this: x0, x1, W0, W1. We'll pass it through the summation unit. We'll pass it through the activation function. It will produce some output. Okay, let's call it the actual output. Okay. Okay, there will also be one input B over here, which is the bias. Think of the bias. It can shift the curve up or down. Okay. And B is also randomly initialized. Okay. And then our target, which is coming from here, will be given to the loss function. And the loss function will produce some loss L. Okay. So let's take a look at, for example, in our case, oh, come on. let me move this so that, yeah, all right. Okay, so what will be the equation for the loss? Loss, you can see, will be, if we are using mean squared loss, if y is what we are calling the target, so this will become y minus a square, right? So like I was saying, our update equations, our learning equations will be what? We have two weights, right? So our learning equation will be W0 equal to W0 minus the learning rate. Okay, whatever we pick, for example, it could be 0.1 or 0.01, right? So this is learning rate times partial L over partial W0. W1 equal to W1 minus the learning rate partial L over partial W1. And similarly to the bias, B equal to B minus the learning rate partial L over partial B. Okay, so now further, let's figure out what is partial L over partial W0. Okay, so the way we will compute the actual values is, let me call this S for sum. Okay, so what, if you take a look at this equation for S, can you tell me what is the equation for S? Remember, it multiplies x0 with W0. So x0 times W0 plus x1 will get multiplied with W1 plus 1 will get multiplied with B, right? Okay, then it will pass through the activation function. Okay, let me pretend the activation function is completely linear, like a slope of 1. Okay, so now the question is, how do we know what is partial L over partial W0? Okay, so if we take a look over here, let me use a different color. So think of it this way. We are starting from here. We are going backwards. And we want to know, how is this loss changing with respect to W0? Okay. So in the mathematics of these change with respect to a loss, so whenever we are passing through like a series of these functions over here, the way it works is, what we do is, to compute partial L over partial 0, we break it into its components. Think of it this way. From here, first we'll go up to A. Okay, so we will first do partial L over partial A, right? Then from here, we'll go over here. From A, we'll go to S. So we'll multiply it by partial A over partial S. Okay, then from S, we will further go to W0. So we'll further multiply it by partial S over partial W0. To show you that the right-hand side is exactly the same as left-hand side, you can verify it. AA cancels, right? And SS cancels. Isn't the right-hand side same as, right? So if we break it into a sequence of partial derivatives, we can easily calculate this. Okay, so now let's go over here. What is partial L over partial A? So now focus on this part. Okay, from your math background, you'll remember if I'm taking partial L with respect to A, okay, first I will reduce this power. So this will become 2 times whatever this y minus a's derivative is. So 2y minus a, right? So remember, let me refresh your memory. If I say y equal to x cubed, and if I say what is dy over dx, remember first you bring 3 down and reduce it, okay? But what if I gave you y equal to x minus 2x plus 3 cube, okay? What is dy over dx? So first you will bring this 3 down, and you will write whatever this is, x minus 2x plus 3 square, right? Then further you have to multiply it by the derivative of the inside. Okay, sorry, let me make it x squared. So you can see the derivative of x squared minus 2x is 2x minus 2. So we further multiplied by the derivative of the inside, okay? So same thing over here. What is the, as I brought this 2 down over here, this became 1. I further have to multiply it by the derivative with respect to minus y minus a. What is the derivative of y minus a with respect to a? -1. Okay, so this will become -2 y minus a. So -2 y minus a is basically partial L over partial a. Okay, now let's go to partial a over partial s. Okay, if I assume the activation function is linear with a slope of 1, then the derivative is 1. Okay, so you can see this is just 1. Okay, what about the last term, partial s over partial w0? If s is defined like this, when we say partial, which means if the variable is not w0, we treat it as a constant. Okay, so if you do now partial s over partial w0, all of this will disappear. 1b x, because they will be treated as constant. Only thing we'll focus on is w0. So what will be partial s over partial w0? x0. Okay, so you can see this whole thing becomes just x0. So partial L over partial W0, what I'm trying to say is the value of all of this is -2 y minus a times x0. Okay, is x0 given to us from the training data? We will already know x0. Okay, what is learning rate? It's 1, or 0.1, let's pretend, is our lambda. Okay, so we know this part, we know this part. W0, remember in the beginning was randomly initialized, so we know this part. Okay, so we can change it after we pass the data through the system. So anyway, the actual output, as you can see, was produced when we passed the training data and we found this number. Okay, so same way as if you go over here, we can calculate this. What is partial L over partial W1? This part. Again, you'll break it into 3 parts. Partial L over partial A over partial S over partial W1. We already know what is partial L over partial A, which is -2 y minus a, right? What is partial A over partial S? 1, because we assumed slope of the activation function is 1. What is partial S over partial W1? So go into the equation for S and now do a partial with respect to W1. So what will it be? X1. Okay. As we do the forward pass, we already know A. From the training data, this is, remember, Y was our target. So we already know this. So we know exactly how we will update this W. In the beginning, it was randomly initialized. This is how we will change it, right? Same thing for the B. Okay, let's try to find partial L over partial B. Okay, so what is partial L over partial B, right? Again, break it into three parts. Start from here and end up at B. So you can see this will be partial L over partial A from L to A. Then, sorry, partial A over partial S, then partial S over partial B. Okay, we already know these two. Minus 2y minus a times 1, right? What about partial S over partial B? If you take a look over here, B, so it's 1. Okay, so in other words, the value of partial L over partial B is minus 2y minus a. That's it. Okay. So now we can write a Python code to go through a loop, and we will repeat this many, many times. Meaning repeat these calculations for training data. Okay, so let's say in our training data, we were given 10 training pairs, meaning 10 sets of X and Y and the corresponding target, right? So as you will see, as you program it, we won't go through it like 10 times. These 10 times will further be repeated like 1,000 times or 10,000 times for it to learn. So as you will see, training is slow. We have to repeat it many, many times. Then it learns and starts to give us the right answer. Okay, so your first assignment will be, let me show it to you. Okay, yeah, in the old set of lectures, it was assignment 2. So I will update that. It will be, okay, so as you can see, you'll be programming this simple single neuron. Same example that I covered over here. Let's see if the training data makes sense. Okay. Let's pick some number over here. Let's pick 1, 2, 3, 4. Focus on 4. Okay. The corresponding Y value, 1, 2, 3, 4 is this one. Okay. The corresponding target. So first, just by looking at if we feed in 4 and 8.6, remember the equation is 2x plus 0.3. Okay, so my question is 8.6 below the line or above the line? See if you plug in 4, right? This is 4. So 4 times 2, 8.3, but the Y given to us is 8.6. So what category should it belong to? 1 or 0?
1.
It's above the line, right? 8.3 is exactly on the line. So if it is above, it's 1. So go to the fourth value in the target. So Y is, like I said, is our target. Okay, So if you go to 1, 2, 3, 4, you'll see the target is 1. Okay. So that's how I just, created 10 values for training. Okay. So you will write the equations just like I have given you step-by-step instructions, how you will create it, write the program. Okay, so as you can see, this is our forward pass. W0 times X0, W1 times X1 plus B is our forward pass. Then the loss, the only thing I did is, rather than having the loss to be Y minus A square, this way the derivative will come out to be minus 2 y minus A. I added this 0.5 over here so that 2 and 0.5 cancel, just to make it a little bit easier. Otherwise, it's the same. So all the derivatives over here, just like we went over, you can confirm they are proper. The 3 equations that we came up with that will update the 2 weights and the biases. And like I said, you'll repeat it many, many times. Then you will test for some unknown data to see what output it produces. Remember the output it produces, if I show you, will be, for example, in the first example, the output is 0.74. Okay, it will not be exactly 1 if it's above the line. So the way we will do it is if it is greater than 0.5, the network is predicting to be above the line. If it is less than 0.5, it's predicting to be below the line. Okay, so 2.7 input 6, remember was 2x plus 0.3. So if we are feeding in x of 2.7, if you multiply by 2, this will become 5.4 plus 0.3 will make it 5.7. But what is the y given to us? 6, which is bigger than 5.7. So what should be the expected output? 1 or 0? See, the actual exactly on the line is 5.7, right? Corresponding to x of 2.7. But the data is 6, which is above 5.7. So it is above the line, so it should predict greater than So you'll see 0.74 is what it predicted. So it is starting to learn properly. Okay. And similarly, if you take a look at the second data, 5.3 and 10.4, what is exactly on the line with x of 5.3? What number? 2 times 5.3 is 10.6 plus 0.3, 10.9. 10.9 is exactly on the line, but what is the y given to us? Which is below the line. So it should predict it to be below the line. It predicted 0.06, which is less than point. So it's predicting correctly. So you'll test it out. And any questions you run into, like I said, even if you, go slowly, some things are not making sense, stop by my office. I strongly believe, doesn't matter which field you are learning. If your foundation is weak, you'll never be good in that field. Okay. So all these, how is it learning? What exactly it's doing? Why are we implementing Wi equal to Wi minus lambda partial L over partial Wi? Why is it minus? Why cannot be it plus? Okay. See, later on, for some of you, as you guys take advanced deep learning, we'll take a look at the security side of AI. And there's a concept called adversarial machine learning, where what we do is we give a picture, for example, of a cat to a neural network. Okay, suppose it recognizes it as a cat, perfectly fine. As I will show you in the advanced course, what we'll do is we'll slightly add noise to it. To a human, it exactly looks like a cat. But what will happen is network will recognize it as a dog, even though it's a picture of a cat. Okay, so there, how do we add this noise to fool the network? What you will see is we change this to a plus. Okay, not a minus. So why? Okay, as you can see, the loss, if you initialized over here, right? To learn it properly, which way do we want the loss to move? If the initial weights are here, to the left or to the right? For proper learning, we want to make it go this way. But to fool the network, we want it to go the opposite way. So that's where we change this minus to a plus, right? So anyway, let me stop at this point for today. One more piece of information that when you program it, some of you took the Python class and perhaps, depending on the professor, some people like PyCharm, some people like VS Code. Some people, I prefer Visual Studio for one reason, because I can use Visual Studio for many different languages, C++, C#, Python, and I really like the debugger in Visual Studio, as I will show you in the next lecture, because it doesn't matter how good you are, everybody will make a mistake as they are writing the code. So the difference between a good software developer or a good AI developer is not how quickly you write the code, but how quickly you debug the code. And if the development environment has excellent debugger, it will save you so much time in figuring out why it didn't work, right? So if you go to the website, okay, if you go to the handouts, and by the way, I'll create one more link over here, Video Lectures 2024, so that today's lecture will be uploaded by tomorrow, hopefully. First handout you will see is software installation instructions, Visual Studio, PyTorch, OpenCV. We'll be using all of these. So if you click over here, I provided a step-by-step instructions, how you'll set up Visual Studio. If you have a Mac, then Visual Studio will not work for you. Then you can use VS Code, which is very similar to Visual Studio. But if you have a Windows laptop, then whatever instructions I gave you will work. The Anaconda instructions are slightly different because I created this handout about maybe a year and a half ago. I updated it, but I looked at it a week ago. They've changed a few things. So don't follow it today. Give me, I will send you a message over Canvas that I have updated the installation handout. Some of you may already have Visual Studio ready to go, maybe in some of the courses. So you'll follow the instructions to have the Python environment, the Visual Studio. I've given you all the details. Wherever I show you, for example, the PyTorch version is changed, and I'll try to put the latest, but you will be picking the latest of all of these, right? And there was one more thing I wanted to mention. Let me try to remember. Okay, so yeah, so what I'll do is, like I said, I'll update it and send you a message over Canvas, then you can set it up. Oh, yeah, the last thing. Let me quickly show it to you. Some of you may be coming to this course perhaps with not as good of a Python background. So I will also send you a message. Some time ago, I had taught the Python class. Okay. And if you can go to a few lectures, few handouts, especially what are lists, what are tuples. Some of these are the dictionaries and so on, sets and dictionaries. So up to this Python part 4 and few lectures, just in case your Python background is not as strong. So I will again send you a Canvas message, give you the link and information and so on. So you can review some of the Python in case you feel. Some of you I know are very good in it, so you can start right away. Okay. All right. So for today, I'll stop at this point unless you guys have any questions. For which one? Yeah, so I'll put it on the Kiwi website as well as I'll upload on the Canvas. You'll be submitting it on Canvas. Yeah. So look for my detailed message.
Sir,
Yes.
so in the last sem, we tried to install these PyTorch in our laptops from your end, and we also did some different version of different kind of environment for the computer vision, and these two environments we didn't have a proper structure. Once we install other environment, one of your environment stop working.
Yeah, so you can create one more environment. So you can have multiple environments. You can name the new environment with a different name. And when you are running Visual Studio, you will select the proper environment. I'll put that in the handout.
Thank you.
Okay.